All right, this is Honors Algebra 2 Pre-Calculus. We're doing 6.5 in Pre-Calc, which is the trigonometric form of a complex number. So in the last video, we talked about how to find the absolute value of a complex number, and we talked about plotting it on a complex number on the imaginary and real axes, which we did. So now what we're going to talk about is the trig form of a complex number. But again, rather than just hand this to you, what I want to do is I want to show you where it comes from, because I think it makes a lot more sense if we can think about something logically, right? So if we look at this triangle, right, I've plotted z equals a plus bi, and I know that means that I am at the coordinate a comma b, right, because my x is my real axis and my y is my imaginary axis. And I could actually draw a little triangle there where I have this hypotenuse that, as we saw in the last example, is really just the absolute value of my complex number. It's the absolute value of z. And the two legs are a and b, and because obviously my horizontal and vertical axes are perpendicular, I could realize that this is a right triangle, right? So if I use SOHCAHTOA, what I want to point out is that the sine of theta is b over the magnitude of z. So for lack of a better way to say it, the magnitude of z times sine of theta is another way to write my b, right? And my cosine of theta, right, should be a over that magnitude of z. If I multiply that over, the magnitude of z times cosine theta is my a. So what I want to point out is that I could rewrite z equals a plus bi as z equals a would be the magnitude of z times the cosine of theta, plus b would be the magnitude of z sine of theta, right, times I, right, because bi. Now, if you factor out that magnitude, because there is a GCF there, I could take that it's the magnitude of z times cosine theta plus I sine theta. And this is the trig form for a complex number, right? So some complex number z is the magnitude of z, right? And sometimes you'll see that called r because they'll talk about this being the radius measured from the origin, and that's fine. But the magnitude of z, cosine theta, plus I sine theta. And that's essentially our formula, right? It also makes a lot of sense if we think back to our unit circle, that y on the unit circle is the sine of theta, and x on the unit circle is the cosine. So it makes sense that the I, which is on the y-axis, the imaginary axis is the y one, would fit with the sine theta, and the x would fit with the cosine theta. So this is fundamentally our formula for the trigonometric form of a complex number. So now, what you'll see frequently is that a lot of times, instead of calling this z, they'll call this r for a radius. So the way you'll see this in a lot of books is, instead of a magnitude of z, you'll see this as r cosine theta plus I sine theta. And I just said magnitude of z when I meant absolute value. Sorry, we were doing vectors in like one video back. So a couple things. When we call, so these have some specific names, and I don't think you're going to use them often, but just so that you're aware that they exist, right? So this r is called the modulus of z, right? And this theta, which I'm looking for a different color, right? This theta is called, so theta is the argument of z. Now, I'm not going to test you on knowing either of those words, but that's what those things mean. Now, some of you might say, okay, but Hogan, how on earth am I supposed to find theta? Like, you gave me, I can find the magnitude. I know a and b. I can find the magnitude of z. Well, the way you're going to find theta, right? So if we think about it, we already know that r is the same as the absolute value of z, right? Which is the square root of a squared plus b squared. So that's pretty straightforward. But we know how to find theta too, because so far we've used Pythagorean theorem and we've used SOHCAHTOA. Well, the thing we're missing is TOA. The tangent of theta is going to be b on top of a. So if you need to find theta, you can find it by doing the arctan of b over a. All right, so that's the trig form of a complex number. So what we're going to do now is we're going to do a quick example where we write a complex number in trig form. So we're on example 2. All right, so I'm going to let z equal... let's do, I'm gonna pick, I'm gonna pick 3 plus 3 root 3 I. Yeah, I'm cool with it. That works for me. All right, so I'm going to pick 3 plus 3 root 3i. All right, so I want to write this. So we're going to write this in trig form. All right, so couple things are going on here, right? So the first thing, right? So the first thing I need to do is I need to find r, right? So I need that absolute value of z, which is the same as r. Well, that's going to be the square root of my a squared, which is going to be a 9, plus my b squared is going to be a 9 times a 3, right? So that's going to be a 27, right? So this is going to end up being the square root of a 36, which is totally a 6. So I get r is 6. Great. Okay. The second thing I need is I need theta, right? So I know that tangent of theta is apparently the b on top of the a, right? Which is just a root 3 over 1. But we know that this is actually something on the unit circle. Now, if it weren't, you could just do an arctan and that's fine, right? So I say, wait a second, this is where I have a root 3 over 2 as my y on the unit circle and a 1/2 as my x on the unit circle. And this is important, they have the same sign, right? So if I inch this over for you a sec. Now, the reason that's relevant is they might not both, it happens in this case that both of them are positive, and we can talk about why in a second. But I asked myself, cool, well, where is the y on the unit circle, root 3 over 2, and the x in the unit circle, 1/2, and the signs are the same? Well, that's here, right? That's here at pi over 3. Right? And also here, where they're both negative, at 4 pi over 3, right? So the trick here, right, is that when I look at these coordinates, I notice that both A and B are positive. Well, if A and B are both positive, I have to be in quadrant 1. So there are actually 2 ways to do this. I'm going to walk you through the 2 different options, right? So option 1 is to use r is 6, right, and use a theta of pi over 3, which is in quadrant 1, right? So pi over 3 is in quadrant 1. So then my answer z would be 6 times cosine of pi over 3 plus I sine of pi over 3. Now, you could have also used 60 degrees. I went with radians. You could totally go with degrees if you wanted. If it's not specified, that's fine, okay? But there is actually a second option. There's a reason that a lot of textbooks will call this r instead of the absolute value of z. So r is in theory a positive number, but let's say I picked the wrong angle. So this is saying face this direction and walk 1, 2, 3, 4, 5, 6 units. That's what this is saying face pi over 3 and then walk 6 units as r. What if I had faced the wrong way instead? If I faced 4 pi over 3, instead of walking in the correct direction, I'd need to walk backwards. So another way you could see this written is use the opposite of r, saying walk backwards, and you could see it as a cosine of 4 pi over 3 plus I sine of 4 pi over 3. Now, I wouldn't suggest it, right? This is also okay, but it's going out of your way when you don't have to. So this is by far the better answer. Now, if you were to distribute that 6 and replace cosine of pi over 3 and sine of pi over 3 with their values, you would find that, in fact, you do get z equals 3 plus 3 root 3 times I. So that's example 2.